At least maximum 100 will be. Hi, hello students. Good evening everyone. I hope all are doing well. Anyway, warm welcome all of you to the Infinity Learn JEE YouTube channel. This is me Surya, your chemistry faculty from Infinity Learn. I believe I am perfectly audible and visible to each and everyone present over here to watch this particular session. Then finally, we are moving to the last part of this particular chapter, that is thermodynamics. We will be starting with the laws of thermodynamics, right? So we studied about the zeroth law of thermodynamics, first law, second law. Now we will be moving to the third law of thermodynamics. Before that, there is a gentle reminder about the AITS. AITS for the JEE Main Session 2 and JEE Advanced. You will get a special discount of 2,999 using this YouTube 50 off. I hope everyone enroll the course first. If anyone missed, just enroll first. Okay, fine. Now we will be moving to the main topic of our today's session, that is the third law of thermodynamics. What do you mean by third law of thermodynamics, right? In the case of second law of thermodynamics, we have already studied about the new term, that is entropy, that is the degree of disorderness, right? Hi Anish, good evening. Yes, I'm fine. Some health issues are there. Okay, fine. So in this particular session, which means that in the third law of thermodynamics, we will be introducing the another term, that is the absolute entropy, right? Absolute entropy. So we can state the third law of thermodynamics as the temperature of the substance approaches absolute zero, right? Absolute zero. Then entropy become a constant, or we can say that delta S is equal to 0 at absolute temperature. Right? This will be the statement for the third law of thermodynamics. Now I hope you must have an idea about the temperature scale. We can say that absolute temperature means it is at the 0 Kelvin. Otherwise we can term it as minus 273 degrees centigrade, right? Minus 273 degrees centigrade or degrees Celsius, or we can term it as 0 Kelvin. So we can predict third law of thermodynamics as whenever the temperature of the system approaches absolute zero or 0 Kelvin, then entropy become constant or delta S value equal to 0. This will be the definition for third law of thermodynamics. So that we are introducing the term absolute entropy, right? So we can say that the entropy of a perfectly crystalline substance. Perfectly crystalline substance means there will be the proper entropy, right? Or disorderness will be very low. So we can say that entropy of a perfectly crystalline substance is 0 at absolute zero temperature. 0 at absolute zero temperature. Clear? So by the use of third law of thermodynamics, we will be just introducing the absolute entropy of a substance, right? That's all about the third law of thermodynamics. Now we will be moving to the next part of thermodynamics, that is the thermochemistry, right? Thermochemistry. Yes. In terms of thermochemistry, we will be discussing about few more terms about the enthalpy. The first one, it is the reaction enthalpy. We have already discussed in your previous sessions about the enthalpy change, right? So here we are introducing the reaction enthalpy or heat of reaction. So we can predict as, for example, if I am taking a chemical reaction here, which means that reactants is converted into products. So we can say that for this particular reaction, we can find out the enthalpy change as reaction enthalpy, and it is given as delta H is equal to sigma. Sigma means summation AIH product minus sigma BIH reactants. For example, I am taking a reaction here. Okay, if this will be our reaction, we can say that small letter A, B, C and D are the stoichiometric coefficients of these reactants and products. So I can return the change of reaction, or reaction enthalpy is equal to right? This will be the expansion of reaction of enthalpy here. This capital small letter c refers to the stoichiometric coefficient of C, right? C is the product here. So small letter c into delta H formation of dC plus D into delta H formation of D. This is the product side, right? Sigma AI H product. This will be the term. Then about the reactant. A stoichiometric coefficient into enthalpy of formation of A plus B into enthalpy of formation of B. This will be the expansion of reaction enthalpy for this particular reaction. There is no need to by heart this formula. Whenever you are getting any numerical problems, you will find out using this formula, right? Clear? Fine. Now we will be moving to the next another terms which is important about the enthalpy. Depending upon different processes, we will be getting new terms about the enthalpy. Here the first one is the enthalpy of formation. The name itself suggests that it is the enthalpy change happening during the formation of a reactant or product, right? For example, at a constant temperature, the amount of heat absorbed or liberated when 1 mole of a substance or a compound formed from its elements is known as enthalpy of formation. Simply you can remember like this, it is the enthalpy change happening whenever a product or compound is formed from its elements, right? That will be the enthalpy of formation. This term is very important for 1 mole of substance. Clear? Yes, fine. Now we will be moving to the standard enthalpy of formation, which means that in every problem in the thermodynamics or thermochemistry, we will be discussing about the standard enthalpy of formation, which means that similarly the enthalpy of formation, but it will be expressed in terms of standard states. What do you mean by standard states? There will be a specified temperature and condition. Specified temperature, that is 298 Kelvin, then 1 bar pressure, right? 298 Kelvin temperature and 1 bar pressure condition is known as the standard state. So we can predict or we can define the standard enthalpy of formation as enthalpy of formation of a reaction in terms of standard states. Clear? And it is denoted by delta H naught F. F stands for formation. This naught stands for standard state. Clear? So depending upon the reaction, we may have positive or negative standard enthalpy of formation. You can see some examples here. Okay. First one is the formation of ammonia. Ammonia is formed from nitrogen and hydrogen, right? As we already know, the equation for the formation of ammonia is N2 plus 3H2 gives 2NH3, right? So in terms of standard enthalpy of formation or the enthalpy of formation, we will be discussing about for the 1 mole of substance, right? 1 mole of product is forming. So in order to make this equation, to get a 1 mole of substance, I am just dividing these terms with 2. So it will become 1 by 2 N2 plus 3 by 2 H2 gives NH3. Which means it will be the standard enthalpy of formation of ammonia, that is given as negative 46.35 kilojoule. Right? Clear? The next example is about the formation of SO2 molecule. S rhombic plus O2 gives SO2 gas. Delta H formation is negative 297.5 kilojoule. Then for NO molecule, right, half N2 plus half O2 gives NO gas. Delta H formation is equal to plus 90.4 kilojoule. So as you can see over here, delta H value or the enthalpy of formation can be positive or negative depending upon the processes, right? The main thing you have to be noted that always whenever we are discussing about the standard enthalpy of formation, the product should be formed will be 1 mole substance or 1 mole product, right? Now in the previous classes we have already discussed about the thermochemical equation, right? So one more I am giving the reminder here, thermochemical equation. Which means that a balanced chemical equation, right? For example, if I am taking this equation here, a balanced chemical equation along with their physical state including allotropic form. Here sulfur is in the rhombic form, allotropic form. Then it is balanced equation, physical state is mentioned here along with the delta H value. It will be an example for a thermochemical equation. Clear? Now let me move to the next type of enthalpy, that is depending upon the process enthalpy change will be different, right? So if I am taking the combustion reaction, what will be the standard enthalpy of combustion? Okay, as you already know what you mean by combustion, right? Whenever any of the substance that combines with oxygen, it will form the respective oxide. That process is known as combustion. So if I am taking any of the combustion process, I can say that the heat exchange, whether it is absorbed or liberated during that process, is known as the enthalpy of combustion. Then important point is that for 1 mole of substance, 1 mole of substance, that is the enthalpy of combustion. Then there is no need to worry about the sign of enthalpy here, which means that combustion reaction is always exothermic, which means delta H value is always negative, right? So that you can see some examples here. Here the first case is the combustion reaction of ethanol C2H5OH liquid plus 3 oxygen gives 2 CO2 plus 3 H2 combustion reaction, right? Then delta H value is given here minus 1367 kilojoule. Similarly, the combustion of carbon give carbon monoxide, delta H value is minus 110, right? Minus 110 kilojoule, which means that this is exothermic reaction having delta H value of negative. Clear? Now the next term about the enthalpy is the enthalpy of solution. As we already know how a solution is becoming, right? By adding solvent and solute and solvent, right? For example, if you are taking 1 mole of substance, again 1 mole is important, 1 mole of substance dissolved in specified amount of solvent. Specified amount of solvent, the quantity of heat absorbed or liberated is known as the heat of solution or enthalpy of solution. Right? In general, we are taking the solvent as water molecule. For example, you can see here magnesium sulfate, right? Magnesium sulfate, whenever it is dissolving in the water, it will form its aqueous form having the delta H value of minus 84.42 kilojoule because it is exothermic. Then for ammonium chloride, dissolution of ammonium chloride in water, it will form the aqueous ammonium chloride having the delta H value of plus 16.3 kilojoule, means it is endothermic. Are you getting my point? Okay, fine. Now we will be moving to the next type of enthalpy, that is about the bond enthalpy. We have already discussed in our third chapter, right? Periodic classification of elements, and also in chemical bonding. Right. What do you mean by bond enthalpy? Something related to bond, right? So we can say that there will be 2 types of enthalpy, that is one is bond dissociation enthalpy and another one is average bond enthalpy, right? The bond dissociation enthalpy can be defined as in a gaseous diatomic molecule. In a gaseous diatomic molecule, the enthalpy change involved in the dissociation of 1 mole of covalent bond, right? 1 mole of covalent bond to produce gaseous atoms is called bond dissociation enthalpy. Simply, it is the enthalpy change happening whenever there is a bond dissociation happens. Right? These are the examples. H2 molecule, right? This is a diatomic molecule. Whenever we are giving some energy to here, it will break into 2 hydrogen atoms, right? So delta H value is equal to 435.0 kilojoule per mole. Then for chlorine atom, it is delta H is equal to 242 kilojoule per mole. Right? This is for the specified case for diatomic molecule. Now, whenever we are taking about the polyatomic molecule, right? More than 2 atoms, like CH4, PCl5, XCF4, there will be the bond enthalpy, but it will be taken as the average bond enthalpy. Here you can see over here, the general equation for the dissociation of CH4 is given here, which means that it contains 4 different steps. So, we can find out the final bond enthalpy of the CH bond in the CH4 molecule is the average of these 4 values, right? Adding 427, 439, 452, 347 all divided by 4 will get the final average bond enthalpy of CH4 molecule, right? It will be 416.25 kilojoule per mole. Clear? Here is the next term about the enthalpy, that is the enthalpy of atomization, which is given by delta H atomization. Again, this is the enthalpy change happening in when it is required to dissociate 1 mole of a pure substance into their gaseous atoms. 1 mole of a pure substance into their gaseous atoms. That is the process of atomization, right? So, here you can see the examples. Yes, sodium, right? Sodium is converted into their atoms. Okay, atoms will form the atomization is equal to 108.4 kilojoule per mole. Similarly, for hydrogen atom, hydrogen molecule, right? H2, 2 hydrogen atoms are present. Whenever it is undergoing atomization, it will form atoms that having the energy of 435 kilojoule per mole inverse. Similarly, for methane atom, it will equal to delta H atomization is equal to 1665 kilojoule per mole. Hi Aryan, good evening. Now, the next term is about the enthalpy of hydration. What do you mean by hydration? Something related to water, right? Adding water. Okay, hydration means it is the addition of water, right? Hydration means addition of water. So we can define the enthalpy of hydration as it is the enthalpy change when 1 mole of the anhydrous salt, which means the salt does not contain water molecule, is known as the anhydrous salt. Whenever this anhydrous salt is combined together to form the hydrate, is combined with water to form its hydrate form. At the time whenever it is liberating or absorbing the heat, that enthalpy change or heat of reaction is known as the heat of hydration or enthalpy of hydration, right? So, you can see the example here. I am taking the anhydrous copper sulfate. It will not contain any water molecule. So, whenever we are adding more water to it, it will form their hydrate form, CuSO4.5H2, by using the energy of minus 78.2 kilojoule per mole, which means that the energy is liberating, right? Energy is liberating. So, we can say that it will be negative value. Clear? Yes, water addition, right? Water addition is the process of hydration. So, we can predict the enthalpy of reaction according to their reactions, right? Enthalpy of different reactions according to their reactions. The next term is about the allotropic form and phase transition. Again, the name itself suggests that it is the enthalpy change happening when 1 mole of substance changes its physical state or phase. As you can see over here, right? Carbon solid is changing to carbon gas. Phase change is happening, right? Solid to gas. So it is having the energy of plus 1439 kilojoule. Similarly, if there is a change in their allotrope, I hope everyone familiar with the allotropes of different compounds, right? For example, if I am taking here sulfur, alpha, beta allotrope forms are there. So here it is converting the beta form of, the beta form of sulfur is converting to alpha form, having the energy of minus 2.5 kilojoule. So this delta H value is known as the enthalpy for allotropic transition. Right? Clear? Yes. Now the next term is about the enthalpy of sublimation. Now you must give me the answer about what do you mean by sublimation. What is the process of sublimation? Okay, Aryan, tell me what are the allotropes of carbon? If you are familiar with, just give me the idea. Carbon is having different allotropes, right? Okay, graphite, diamond are the different allotropes transition. So we can say that, for example, we can say that there will be the transition of graphite to diamond form. So that enthalpy change happening between graphite to diamond allotropic transition, it is known as the enthalpy of transition for carbon in terms of graphite and diamond. Clear? Aryang? Yes, the process of sublimation is known as the conversion of a solid substance into gas without going into their liquid state, right? In general, there will be the transition from solid to liquid, liquid to gas, right? But in the case of sublimation, there will be the direct transformation or direct transition of solid to gas form. For example, you can see here, this is example, iodine, right? This will be gas. Iodine is changing its solid state to gas state without forming any dissolution, right? Yes, without forming to the liquid state. So we can say that this is the process of sublimation. The energy change happening here or enthalpy change happening here is the enthalpy of sublimation, and it will be written as delta H sub, right? Again, the 1 mole of solid substance. 1 mole is compulsory. Clear? Yes, decomposition of naphthalene bond, because naphthalene is also a sublimated substance, right? They can also undergo sublimation. So we can say that decomposition of naphthalene bond is also an example of enthalpy of sublimation. Right? Clear? Yes, fine. Now we will be moving to the most important topic from the thermochemistry part, that is the Hess's law of constant heat summation. Hess's law of constant heat summation, right? Ready? Yes. As we already know, enthalpy we have studied, right? Enthalpy is a state function, which means that it depends on initial and final state only, not on the path. So we can say that whether the process is happening in single step or multiple step, we can say that the enthalpy change should be same, right? Enthalpy change should be same whether it is happening in single step or multiple step. So this term is defined by the Hess's, by a law known as Hess's law of heat summation, and it is defined as the total enthalpy of a reaction or complete course of a reaction. Total enthalpy change during the complete course of a reaction is same whether it is happening in, whether it is take place in one step or several steps, right? Are you getting my point? Now we can define the Hess's law of heat summation by using the examples here. For example, if I am taking a reaction here, I can say that these A can be converted into product in a single step, right? This will be the first step. So I am taking the delta H value here. For example, it will be Q, right? Now if I am saying like that, this A is converted to product by multiple steps, right? First it is converting to A to B, then B to C, then C to P, right? So for example, if I am taking the first enthalpy is equal to delta H1 is equal to Q1, delta H2 is equal to Q2, then delta H3 is equal to Q3, right? Then according to the Hess's law of constant heat summation, we can say that the change in enthalpy should be equal. For example, I am taking here the delta HQ is equal to delta H1 plus delta H2 plus delta H3, right? This will be the mathematical explanation of Hess's law of heat, constant heat summation. Clear? Yes, Q1 plus Q2 plus Q3 or the summation of individual enthalpies H1, H2 and H3, right? Now, based on the Hess's law, there will be some applications. Okay, fine. What happened? Anish, is that clear? Okay, no need to worry. Once I complete the session, just go through the complete classes, make the preparing notes and practice the questions. That will be easy. Okay, now we will be moving to the applications of Hess's law. First one, it is the determination of heat of formation of intermediate compounds which are unstable or which cannot be isolated, right? For example, I am taking here heat of formation of carbon monoxide. It will happening in two steps. First one, it is the graphite form. Carbon in the graphite form undergo combustion to form carbon dioxide, having the delta H value of, this will be having delta H will be, I can write it as delta H is equal to minus 393.52 kilojoule, right? Is there any doubt? Delta H will be minus 393.52 kilojoule. That's why it will become plus here while adding, right? Similarly, in the second step, the carbon monoxide undergo combustion to form carbon dioxide, having the delta H value of minus 283.02 kilojoule. So, in order to find out the formation, delta H formation of carbon monoxide, because carbon monoxide is the intermediate step here, right? In order to find out the heat of formation of intermediate compound, we will use the Hess's law of constant heat summation. So we can take that while taking the difference between these two equations. Between these two equations, you will get the enthalpy of formation of carbon monoxide, right? You can just try it over. You will get that C graphite plus half O2 gas gives carbon monoxide gas having the delta H value of minus 110.5 kilojoule. Delta S will be minus 110.5 kilojoule, which means that this will be an exothermic reaction. Clear? Now there will be another application for the Hess's law, that is the calculation of lattice energies. For the ionic compounds. Whenever we are discussing about the chemical bonding and molecular structure chapter, we have already discussed about the lattice energy, right? Lattice energy. What do you mean by lattice energy or lattice enthalpy? Okay, it is an enthalpy change happening whenever an ionic solid or ionic compound is formed from its gaseous ionic substance, right? For example, if I am taking NaCl here, right? NaCl solid, this is an ionic compound. Whenever it is combining or forming from its constituent ions, Na plus and Cl minus, Na plus and Cl minus, okay, Na plus and Cl minus, the enthalpy change happening in between is known as the lattice enthalpy, or it is given as delta H lattice is equal to plus 788 kilojoule per mole. Yes, it is the energy released during the formation of crystal lattice. For example, we are taking here sodium chloride, right, NaCl, which is formed from Na plus and Cl minus. Yes, okay, fine. Now, we can say that we can find out this value, but it is not an experimental concept, right? It is very difficult to determine the lattice enthalpies of some of the ionic compounds by direct experiment. So, we are using another indirect method by using a diagram known as Born-Haber cycle. Born-Haber cycle. Clear? Now, we will be discussing about the terms in Born-Haber cycle. You can see over here, this will be the outline of the Born-Haber cycle. We are taking the example of sodium chloride here. Our ultimate aim is to find out the lattice enthalpy of NaCl, which is formed from Na plus and Cl minus. Na plus and Cl minus. Right? Okay, I believe this picture was clear. Okay, here is the first step in the case of NaCl. We already know sodium chloride is formed from sodium atom, right? Sodium plus chlorine. So here it is sodium solid plus half chlorine gives NaCl solid, right? So we already know what will be the enthalpy here, whether it is the enthalpy of formation or lattice enthalpy or enthalpy of solution. What will be here? Whenever we are forming any of the compound from their elements, right? What will be the enthalpy called? It will be the enthalpy of formation, right? It will be the enthalpy of formation. So in the first step, I am taking here sodium solid plus half chlorine gives NaCl. Delta H value is around 411.2 kilojoule per mole. That is the enthalpy of formation of NaCl. Now, in the case of formation of NaCl, there will be several steps happening. First, we have to convert. Sodium will be in the solid state, right? Whenever it is forming from the sodium chloride, forming to the sodium chloride, it should be in their gaseous form. Should be in the gaseous form as well as in their ionic form. So first term I have to do that. I have to convert the sodium in the solid state to gaseous form, right? So I am converting here solid sodium to gaseous sodium. What will be that process called? Direct conversion of solid to gas. Sublimation, right? Direct conversion of solid to gas is known as the sublimation. So I can call these enthalpy change as enthalpy change for sublimation, and is given as 108.4 kilojoule per mole, right? Then we have already converted solid sodium to gaseous. Now we have to convert this gaseous sodium atom to their ionic form. What we have to do? We are just adding here. We are just adding electron, right? Hello. Okay, I hope now I am audible. Extremely sorry for the technical error happened. Okay, we will be starting from the lattice enthalpy here. Okay, I hope it was clear for everyone. Okay, first step we have to do that we are just converting the solid sodium to gaseous sodium by the process of sublimation. Then it will be the delta S sublimation given as 108.4 kilojoule per mole inverse. Then in order to change the sodium to ionic form, energy here it will be equal to 496 kilojoule per mole inverse. Then about the chlorine I will be taking here, I am just trying to break the chlorine molecule here. It will form the chlorine atoms. So we can find out that the bond dissociation enthalpy is here, half the delta S dissociation. Then finally we will be moving to the Cl minus ion by giving the electron affinity or electron gain enthalpy. Then after getting these ions we will be forming the finest ionic compound, that is NaCl. This is known as the lattice energy, right? Now then, according to the Hess's law of heat summation, we can say that the sum of these all processes, right, sum of these all processes will be equal to the lattice enthalpy of NaCl. So I can take it as, I will be taking the sum here. First one 411.2, which means the delta S formation of NaCl, plus 108.4, that is the ionization enthalpy, that is the sublimation enthalpy. Okay, this will be the sublimation enthalpy. Then it is adding with the ionization energy, that is equal to 496 kilojoule per mole. Then the next one, half of bond dissociation energy of chlorine, that is equal to 121. Then the next one, electron gain enthalpy, that is equal to plus of minus 348.6. While taking the summation, you will get the final answer around 788 kilojoule per mole inverse, or 788 kilojoule per mole, right? Which will be our lattice enthalpy for the formation of NaCl, that is equal to plus 788 kilojoule per mole. Clear? That's all about the Born-Haber cycle. Born-Haber cycle, which is used to find out the lattice energies for the ionic compounds. For example, I am taking here NaCl. I hope it was clear for everyone. Now we will be moving to the third application of Hess's law, that is the heat changes in phase transitions and allotropic transitions. Same here, we will be taking about the example of diamond carbon and graphite carbon. You can say here, diamond carbon is undergoing combustion to form carbon dioxide having the delta H value of minus 395.4 kilojoule. Then the second step, graphite is converting to carbon dioxide having the energy of minus 393.5 kilojoule. While you are taking the difference between these two equations, that is equation 1 minus equation 2, you will get the answer of delta S transition is equal to minus 1.9 kilojoule. This is also based on the application of Hess's law of heat summation. Clear? Yes, fine. Okay, so far we discussed about the thermochemistry part. We will be starting about the thermochemical equation, which means that the balanced chemical equation having the delta H values along with their physical state, including allotropic form, right? That will be the thermochemical equation. Then we will be studying about the enthalpy of formation, enthalpy of reaction. Depending upon the different processes, we can find out different enthalpy changes, right? Then we will be moving to the Hess's law of heat, Hess's law of constant heat summation, which is based on the summation of heat of enthalpy or heat of reaction for the different processes. That will be the same. And we have seen the applications of Hess's law, including the Born-Haber cycle. Okay, that's all about the today's session. So far we have successfully completed our thermodynamics chapter. Starting from the basis of thermodynamics, we have studied about the different terms around the thermodynamics, right? Different terms around the thermodynamics. You have studied about the system and surroundings. Depending upon the systems, we will be defining the 3 different types of system: open, closed and adiabatic system. Open, closed and adiabatic system. Then finally we will be moving to the different types of processes, right? What are the 4 different types of process? Thermodynamic process, right? These are the different types of processes. Okay, isothermal, isobaric, isochoric and adiabatic. I hope everyone knows the difference between these 4 processes. Then depending upon this process, you will be predict the value of W, right? Work given here. Then we will be moving to the first law of thermodynamics. First law of thermodynamics, which is given by delta U is equal to Q plus W, right? Change in internal energy is equal to the sum of heat and work done. Then depending upon the process happening, we will be giving sign conversion, IUPAC sign conversion to the heat. If the heat is absorbed by the system, we will be taking it as positive. If the heat is liberated to the system, it will be taken as negative. Then if the work is done on the system, it will be taken as positive. If the work is done by the system, it will be taken as negative. I have already covered these sessions, that's why I am going very fast. I'm just summarizing the topic. This will be the mathematical expression for the first law of thermodynamics. Then we will be moving to the next term, that is the enthalpy here. Entropy here, that is the Q reversible by temperature, where Q is the heat and T is the temperature. Then we will be introducing about the term enthalpy, which is equal to the sum of internal energy and the pressure volume work, right? Pressure volume work. Then we will be moving to the Gibbs-Helmholtz equation, that is equal to delta G is equal to delta H minus T delta S. Delta G is equal to delta H minus T delta S. Then we will be moving to the another formula about the heat capacity, right? Heat capacity. There are 2 types of heat capacity, Cp and Cv. You will take a Mayer's relation here, that is Cp minus Cv is equal to R. And finally, we reach into the spontaneous process or condition for spontaneous process. In terms of delta G, that should be negative. In terms of entropy, it should be positive. Then in terms of enthalpy, it should be negative, right? In total, you will get more formula in this particular chapter. Just making the formula sheet for different formulas in the thermodynamics topic, then keep it on your study table. It will be very helpful for you to remember all the things. Then keep on revising, keep on practicing the questions from this thermodynamics topic. Not only thermodynamics, for all the physical chemistry topics, right? Okay, I hope I have covered almost all the important topics from the thermodynamics chapter. The next session I will be coming back with the new chapter, that is the biomolecules in the grade 12. Okay, I hope it was clear for everyone. This completes thermodynamics topic. That's fine. Okay, Maxim, can you please share this session to Maxim to your friends and family also. Then don't forget to subscribe our channel. Do like, share, and share. Then again, reminder about the AATS. Just enroll fast for the AATS. Then see you in the next session. Till then, bye bye. Take care.